So my name is Colin Jones. I'm from the UKSM project. So this is the first of 4 online UK CMIP6 analysis workshops. So before we start, I want to say a big thanks to Hazel and to Poppy that are doing all the technical side of this, and to the rest of the UK CMIP6 analysis team that have helped put this together. This afternoon, and then we'll have 2 more sessions tomorrow at the same times, and then we're aiming for 4 more sessions early in May, and we'll let people know as soon as possible when those sessions are. The way we're going to work it is each speaker has 10 minutes in total, and that ideally includes 2 minutes for questions, so 8 minutes. We should have four slides that outline their poster. After 6 minutes, Hazel will give you a 2-minute warning. Please aim to finish by 8 minutes. If you go over 8 minutes, you will eat into your own question time. To consider speakers coming after you, we will reserve the right, I'm afraid, to mute you if we hit 10 minutes for any individual one. So if you're speaking after 10 minutes, you may be speaking to yourself. Please bear that in mind. Questions you should put through the chat facility, and I will endeavour the best I can to cover some of the questions straight afterwards in the 2-minute slot. If there are detailed questions or more questions, you can add them afterwards to the Google Doc. There should be a Google Doc associated with each session in the invitation, and then try and get the speakers to respond to those later at a later date. I think all your microphones should be muted. It may be an idea that you also turn off your videos if you've got them on, just to keep bandwidth reasonably okay. I think that's all I need to say for the time being. I'm just checking my notes. Okay, I think that's everything. So I'm going to hand over to the first presenter, who should get control of the screen. So Hazel, you'll take this timing from the time Chris starts talking. So this is Chris Smith, University of Leeds. Over to you, Chris.
Okay, thank you, Colin. Hopefully everybody can hear me. I'm going to introduce the effective radiative forcing from CMIP6 models. And this is part of the radiative forcing MIP. So it's one of the 21 endorsed MIPs for CMIP6. And we've had some very good participation from modelling groups. We've had 16 models from 12 modelling groups so far. And I think the reason why we've had such good participation is because our tier 1 experiments are quite light. So we've asked for 6 30-year time slice experiments. So 180 years of atmosphere only integrations in total. So we've had a very good response from the community. And the experiments that we are looking at is we're looking at the present day radiative forcing from greenhouse gases, from aerosols, from land use change, from all the anthropogenic components together, and then also that climate model classic 4 times CO2 as well. And we have these 5 experiments, and we also have an 1850 control, which we use to compare our present day or 4 times CO2 time slices against to determine the radiative forcing. And what we do find in the 16 models that have provided us results so far, where there's a comparable experiment for CMIP5, that the CMIP6 models are actually better constrained in their forcing. So this figure on the right here shows you the aerosol forcing for CMIP6 in orange and CMIP5 in blue. And we find that, that the aerosol forcing is generally slightly less negative in CMIP6. And also there's a smaller range between the models, and we actually have more models participating in the aerosol forcing experiments. For 4 times CO2, we also find that there's the forcing is generally higher and better constrained than it is for CMIP5. And we put this down to an improvement in model radiation parameterization for CMIP6. So this plot on the left here shows you various ways of actually estimating the effective forcing in different models, but the bars to sort of concentrate most on are the 3 on the right for each component. So we have the effective forcing, we have the instantaneous forcing, and we have this adjustment term. And I'm going to talk a little bit more about the adjustments later on, but they're a significant part of the forcing for each component. So this aerosol forcing we can actually look at in terms of each model's climate sensitivity. And what we find is that there's no correlation between either ECS, so the equilibrium sensitivity, or TCR, the transient climate response, with aerosol forcing. So this is interesting because it's showing that the modelling groups aren't using the historical temperature as a constraint to tune their models. If they were, we would expect that there'd be a significant negative correlation, particularly with TCR. So there's lots of literature that's shown that you need a strong aerosol forcing to balance a high TCR and vice versa. And there's also more evidence in this one if you actually look at, I've not shown it here, but if you look at certain models' historical temperature reconstructions, so CAN-ESM, which is model number 1 here, has a sort of moderately low aerosol forcing and a very high TCR and ECS. And their historical temperatures are sort of hitting about 1.4, 1.5 degrees, which is higher than observations. So that's one example of a model that's clearly not using historical temperature as a constraint for their CMIP runs. So moving on, we are looking at the adjustments, so previously known as the rapid adjustments, in a bit more detail here in the various models. So what we do, we use a rated kernel technique. So this is a technique that's used initially in climate feedback literature, and we now extend this to the atmospheric state variables and these fixed sea surface temperature runs to determine what the adjustments are. And what we find is that for greenhouse gas and obviously CO2, which is a subset of greenhouse gas forcing, we find that the stratospheric temperature is the largest adjustment to the total. So total's in black and the stratospheric temperature is in yellow. So this implies that the traditional method of radiative forcing, which was just accounting for the stratospheric adjustment, is a good approximation of the total when we're talking about greenhouse gas forcings. But when we talk about aerosols, we find that the largest component of the adjustments is due to clouds, and the stratospheric temperature term is practically zero. So aerosols, one example where using the stratospheric definition of radiative forcing isn't quite accurate. And this has been known, this was known in AR5, but it's kind of this work and a sort of paper I led 2 years ago that kind of really showed this in detail. We have also as well a breakdown of what clouds are doing to each of these experiments. So,
2 minutes, Chris.
Sure. So as you can see, for greenhouse gases, we have a reduction in sort of low to mid-level cloud fraction, which is driving a strong shortwave cloud adjustment, and you can also see this in the bar here. But for aerosols, what you mainly see is a Toomey effect. You have an increase in aerosol optical depth across the various cloud heights. So this is increasing the shortwave reflectivity and reducing, or leading to a negative cloud adjustment. So my final slide, I'm going to talk about the aerosol forcing in a bit more detail. So we can use a method to break down the aerosol forcing into its aerosol radiation interaction, aerosol cloud interaction components. So again, sort of putting numbers to the aerosol forcing, we find that the mean of 16 models is about just about minus 1.03 watt per meter squared, with a standard deviation of 0.22. So this constraint is quite, or these models are sort of not showing a very big diversity in aerosol forcing, which is really interesting. So I'm just going to sort of conclude here. So this paper currently is in ACP discussions, and hopefully it should be finalised in the next month or so. So thanks for your attention, and I'm happy to take questions now.
Okay, thanks, Chris. Before I go on, can people hear me okay? Yes, is the answer. Okay.
Yes.
So we're waiting for questions in the box. While any of those questions come up, I've got a couple to kick things off with, Chris. So to begin with, just the models that are there, how many of those use the easy aerosol approach, which might have a common aerosol response, I guess? Do you know that? Or
yes, so there are only 2 models that have used the easy aerosol, the MAC SP easy aerosol. So the other 14 all used emissions driven anthropogenic aerosols. Okay,
and I'll ask a follow-up then. And that is, you talked about increased optical depth feeding into the aerosol forcing. Are you able in some way to look in the model sense whether there's a first versus second indirect effect? Can you separate that out in any way?
Yes, we can. We can do it approximately. So, so this method here allows us to determine the cloud fraction contribution to the total aerosol forcing. So this cloud amount term is that the change in cloud fraction. And then we can assume that is part of the second indirect effect of this scattering term. Some of it is Toomey, and some of it is part of that second indirect effect. We can look at the change in cloud liquid water content or cloud water path. And we can apply a simple relationship. So there's a paper out by Ed Grisbeert who looked at this in a number of models, and there's a very good relationship between the change in cloud liquid water path and the second indirect effect. So we use that as part of our analysis of breaking down that aerosol contribution.
Okay, I'm going to give a couple more questions. I think we've got 1 minute left. So there's one question from Peter Cox. Do your conclusions about the difference in aerosol forcing across CMIP depend on the period over which you look at the aerosol forcing time period?
Yes, that's correct, because CMIP6 was I think it was 1850 to 2000 was the period that they were evaluating the aerosol forcing, and CMIP the CMIP emissions have changed, but also it's kind of well understood that the aerosol emissions in 2014 were probably less than they were in 2000. So that is possibly a factor why the CMIP6 aerosol forcing is lower than CMIP5. But what I do think is interesting is that lack of correlation between climate sensitivity and aerosol forcing. And we sort of went into this study hoping we could find out one of the reasons why some CMIP6 models were showing very high sensitivity, and unfortunately we didn't manage to do that with this paper. So that's very much an open question.
Okay, I'm going to ask one last one, which I think can be a yes/no answer, from Rachel Law at CSIRO. Are extra models still useful? Access to doing their RF MIP runs now?
Yes, please. Keep
them coming. That'll be a quick one. Okay, many thanks, Chris. There may be more questions, and people will put them in the Google Doc, hopefully. Okay, we move to the next talk now, which is Rick Williams, University of Liverpool. So hopefully, Rick, you're in control of the slides, and you'll get your 6-minute warning when it comes up, okay?
Okay.
Over to you, Rick.
Thanks very much, Colin. So this is work with Paolo Ceppi and Anna Katabuta. So in the top left figure is an example from 9 CMIP6 models of how surface warming increases with cumulative carbon emissions. And what we can see is there are significant intermodal differences in those slopes. And this is important. It affects our view as to how much carbon we can emit until we meet cross warming thresholds. What's unclear is whether those slopes are being set by the thermal or carbon responses in these very complex models. So we normally use a metric, the transient climate response to emissions, which is formally defined for the 1% annual increase in CO2 experiments, which I've shown here. So that metric is simply the slope of these lines, and I'm defining it by the change in global mean surface air temperature since the pre-industrial divided by the cumulative carbon emissions. Now, to get some insight into the thermal response versus the carbon response, I'm going to expand that into using an identity where the delta T over delta F represents the thermal response, the dependence of surface warming on the radiative forcing, and then a radiative and carbon response, the ratio of that radiative forcing on the carbon emissions. So the next two slides will be looking at each of those terms, and then I'll conclude with comparing with CMIP5. So for the carbon view, we've got different cumulative carbon emissions because of the carbon cycling involving the land and the ocean. The different intermodal differences in the land response are larger, and so that's the main contribution to the differences in the airborne fraction that we see in this middle plot. But my focus here is the contribution to the TCRE, and the dependence of the radiative forcing on carbon emissions, the bottom left plot, declines in time. And that decline in time you can relate to two contributions. One is the ratio of the radiative forcing change and the change in the airborne atmospheric carbon inventory, and that declines in time due to a saturating effect. And then lastly, there's the airborne fraction. So what we can see from that is that intermodal differences, there are quite significant differences because of the differences in how the radiative forcing saturates with atmospheric CO2. So then moving to the thermal response, the radiative forcing is driving a planetary heat uptake, obviously, and then a radiative response, which we express as a product of a climate feedback parameter and a surface temperature change. Now, again, we're interested for the TCRE in this ratio of the surface warming change divided by the radiative forcing, which, using this top equation, you can rewrite as presented in the grey box. So this radiative forcing response, or the thermal response here, it increases in time, and that's due to two reinforcing contributions. One, the climate feedback parameter is actually becoming slightly smaller, leading to a larger increase, and the fraction of the radiative forcing that warms the surface increases due to a decline in the fraction of heat taken up by the ocean interior. Now, what's striking here is there are really quite significant intermodal differences arising from this climate feedback parameter. So to move to my last slide, the top panels here show 9 CMIP6 models and then 7 CMIP5 models. And actually, for these subsets, the black and the grey lines are the appropriate running means for CMIP6 and CMIP5. They're somewhat similar, but what's more striking is the spread is greater for CMIP6 than CMIP5. Now, if you use this identity for the TCRE, you can untangle the reasons why there are these differences. In particular, if you take the relative standard deviation, so that's the ratio of the standard deviation and the model mean, this thermal term is twice as large, effectively the spread for the CMIP6 versus CMIP5 models. If we then turn to the term linked most closely to the carbon cycle, the airborne fraction, that is actually slightly smaller for CMIP6 than CMIP5. Now, these relative standard deviations, you can compare with them with each other to work out how they control the TCRE spread. And it's a much larger contribution for the thermal response for CMIP6 than the airborne fraction response. So our view is that intermodal differences in the TCRE are mainly due to the thermal response, somewhat, at least over this timescale, rather than the airborne fraction for these this subset of 9 CMIP6 models. And that's due to the effects of the physical climate feedback and ocean heat uptake. Now, if you untangle the contributions to that physical climate feedback in this plot that Paolo Ceppi's provided, it's mainly due to larger spreads in the cloud contributions. And so untangling those are central to really understanding these different projections. So this work's was submitted in December to environmental research letters and currently under review. And I'll stop now there. Thank you.
Okay, thank you, Rick. Right, first question is from Piers Forster. Rick, I'm surprised the CO2 forcing should not have such a large difference between models. I wonder if RF results would show this also.
Sorry, it was a bit crackly there. It was a surprise from Piers.
Yes, yeah, perhaps I can ask it because I do not think I kind of typed it in particularly well. What I wanted to know, Rick, was you did kind of show this big dependence of the CMIP6 result with their kind of carbon dioxide forcing not being logarithmic, and there was a big difference between the simulations there, which yes. I found quite surprising.
I'm not saying it's not logarithmic, Piers, but the radiative forcing coefficient A is different.
Yes, so that's what I found quite odd.
Yeah, so it's this slide, I think. We're discussing. That's what comes out about our diagnostics. You know, maybe we should talk offline in more detail.
Yes, yeah, because it looks a very big difference between them, which I found surprising.
Okay, I'm going to come back in. I've taken my microphone off. Does that make me less crackly, Rick?
Yes, that is a little bit better.
Okay, right, and I'll go this way. Okay, a question from Ben Booth. Presumably some of the spread in TCRE comes from non-CO2 forcing, such as aerosols. How does this appear in your framework?
Ben, that's a very good question, and it's not actually formally. Sorry. For the TCRE is defined just for these 1% annual increases in CO2. I fully agree with you that one should be extending this to include the non-CO2 contributions. We have done that for CMIP5 before, and it does make a contribution over the first 10 years. Sorry, there's quite a bit of bad feedback here. Colin, is that better? Yeah. Okay, I'll start again. Ben, you're quite right. I think we should be thinking about these non-CO2 contributions. This particular set of diagnostics have been done on experiments where it's just a 1% annual increase in CO2. So it's that aspect's formally excluded. But we have looked at this for RCP runs for CMIP5, and the non-CO2 contributions are important over the first 20 odd years. They're not the dominant cause of the intermodal differences after about 50 years. Again, for CMIP5, the thermal and carbon responses are comparable to each other, but that's what seems to be different in our diagnostics.
Okay, I'm just looking through the list now. I think we may, unfortunately, I think we're out of time. There are a number of more questions, so if people could put those into the Google Doc. I've gone back to using the microphone because I think I was causing some echo. So please put the other questions to Rick into the Google Doc and can be followed up afterwards, if that's okay.
Thanks very much.
Move on to the next speaker. Many thanks, Rick. So the next speaker is Femke Nissa. I hope I pronounced your name correctly.
Femke Nissa.
Femke Nissa, sorry. Thank you. Okay, Femke, so you'll be told when you've got 2 minutes to go. Okay, over to you.
Yes, thank you. Let's see. Do I have control of the thing already? Yeah. Okay, my talk will be about constraining climate sensitivity. We've seen in the previous 2 talks that the spread in climate sensitivity in a thermal fraction in previous talk is increased massively in CMIP6, and that could concern some of you, but I think from my perspective, using a merger constraint spread is always a lovely thing. Just to repeat the 2 definition of the climate sensitivity, we always talk about the transient climate response, which is the climate response in an idealized simulation of 70 years of 1% CO2 increase, taken an average between the last 20 years. And we've got the equilibrium response that we typically approximate with a 150-year simulation. It's really important to know these things well, because the carbon budget depends on it. We saw that the thermal fraction is the most important thing in determining TCRE in CMIP6, and basically all the other impacts of climate change usually depend scale with climate sensitivity. And it's surprisingly easy to find a constraint in climate sensitivity using the CMIP6 models. This is probably partially due to the fact that the radiative forcing is now more constrained, so that more of the differences between models lie in the feedback parameter. If you look over the entire period, I'm taking a 10-year running mean and the left upper plot. You can see with color coding the TCR values, you can see that it's quite chaotic. You've got a couple of very high sensitive models that warm way too much, but some of the high sensitive models also cool quite a bit during the 1950s to 1970s. So from that period, it's not very easy to find a difference between these models compared to the observations. And I was quite surprised to hear that the aerosol radiative forcing differences are a bit less in CMIP6, because you do see a hugely different response in this 1950-1975 period in these models, where some models heat basically cool down significantly while others continue heating, and this is the period where aerosol forcing was most dominant. If you now look at the right hand plot, that is the warming after 1980, there is a huge distinction between low sensitive and high sensitive models. And you can see that the black observations fall within the sort of the lower half of models, with TCR values between 1.5 and 2. To get a formal probability distribution of TCR from comparing models and observations, we use a technique called emerging constraint, which is quite simply using a regression between a thing you've observed from the past and the variable you're interested in this case, TCR. There's two reasons we trust these emerging constraints to tell us something about TCR, or there's two conditions. The first one is that we want it to be consistent between generations. If it changes a lot between generations, then maybe some of the physical processes are too uncertain, or there might be big systematic errors. Whereas if they are consistent within the later generations, then we probably have enough information or enough trust in these models that we can actually find a consistent relationship. And the second reason we might trust them is if there is very good theoretical grounding behind the relationship. So for TCR and ECS and observed warming, we expect that to be a very linear line, and that's what we see from the regression as well. Getting the actual PDF is simply using the observations where we have some uncertainty around the observations, take the uncertainty around the regression, convolve these two, and you get a nice PDF for the variable of interest. One of the things you always have to take into account is how much of the observational uncertainty is simply from the fact that we don't have enough thermometers. And the second one is that you might have internal variability. In CMIP6, we've got loads and loads of initial value runs. So for each of the models, we can estimate the internal variability really well. But for the observations, we don't have that. So what we do is approximate the internal variability of the observations by the average of the model uncertainty. CMIP6 is a bit more variable than CMIP5. So if you include that, you see that the constraint using CMIP5 is somewhat stronger than CMIP6, but they are very consistent between the two. The 5 to 59% confidence interval is between 1 and 2.1, which is a huge difference compared to what the IPCC said. So the IPCC didn't specify the probability distribution complete, but if you sort of assume it is a normal distribution, you can see that there is a huge spread in that distribution compared to what we can do using a simple emerging constraint.
2 minutes, Femke.
Yes, thank you. For ECS, we have a more difficult thing because we don't expect the relationship between observed warming and ECS to be linear. Using a 2-box model and some approximations, we found a relationship where ECS is related to observed warming via this equation. So dt divided over some forcing parameter, ocean heat parameter, and observed warming. And we can again use that. If you have a too short a period, your regression is really steep, so you can't really get a constraint. And the longer your period is, the more forcing you have observed, the straighter your line is, and the better you can constrain it. We've did some sensitivity analysis. The best estimate we have is an ECS between 1.5 and 4. No matter what we do, we can't get the upper bound of 5 to 59% confidence interval below 4.7, which indicates that loads of these models that we've seen have climate sensitivity that is inconsistent with observed warming. With 12 of the models, 12 of the 34 models in this research having an ECS above 4.5. We can also check the theory again, and we see that this 2-box model is probably not the best model, but it does work to some extent, and we might want to look at a better model of finding it so that we can get the exact line that we need, because the regression is dependent on what functional form we use between the thing we've observed and the thing we want to predict. that was it.
Okay, thank you, Femke. That was well on time. Okay, there's a comment first from Chris Smith regarding to your comment about the aerosol ERF, and that is, he says the present day, by 2014 aerosol ERF is quite well constrained, whereas the 1960 to 1990 aerosol ERF in many models is probably less so. This is a question for RFNIP.
Yeah, so
and he's followed that up with, okay, sorry, do you want to respond to that? Go ahead.
yeah. So we're not estimating radiative forcing directly. We assume that the differences in radiative forcing that are still left are visible within the errors of the regression. We choose a period where the errors in, where the differences in radiative forcing between the models is relatively small. We have to balance that with internal variability. So on the one hand, we want to take a period that is as long as possible, and on the other hand, we want to take a period where the aerosol differences are minimized, and that's why we've come to this compromise of a period between 1975 and 1985.
Okay, I think that might answer Chris's next question, which was how did you estimate the non-CO2 radiative forcing? I think that's answered. Okay, I'm going to take the chance to answer a question as well. So both for the TCR and the ECS, the observation period used covers what we know as the surface warming hiatus quite strongly. So how sensitive would your results be if you were able to use you may not be able to use a different observation period, of course, but if you were able to construct a different observational period that didn't have that kind of hiatus in?
I don't think it has much of it. So I'm not doing a linear regression of warming. I'm comparing two decades, so 1975 to 85, 2009, 2019. There's only a couple of years of that hiatus still in there. If I take the period a bit earlier, so for instance, between 2002, 2012, I do get a lower value of ECS. And we should be able to combine all of these values to make sure that the internal variability is better constrained. So it does matter, but because we take internal variability into account, it's already included into the 5 to 95% uncertainty range.
Okay, and then Peter Cox has a question for him. What is your likely, in inverted commas, range of ECS?
Yeah, he asked me that last week, and unfortunately I've got a bit of RSI, so I've not been able to figure that out, but it should be approximately between 2.2 and 3.4, if I do some computation by heart.
And likely in this case means what?
2/3 of the probability density function within that range.
Right, okay, thanks. All right, then we're just on time, so thanks very much, Femke.
Welcome.
I'm going to move on to the next speaker now, thank you. Okay, so the next speaker is Jeremy Walton from the Met Office. Jeremy, you should have control of the screen, I think, so I'm going to hand over to you.
Thanks, Colin. Just wait for catch up here. Right, so I'm going to be giving an update on the processing of CMIP6 data, the output from the models, and I'll be describing what we've been doing with that and how much is available from experiments run in the UK. My colleagues there are largely responsible for doing the conversion and also for building the infrastructure that's used to do the conversion of model output to CMIP6 data. So my slide here describing with a CMIP6 data, where does it come from? As I said, it's produced by converting the output from the models. I'll tell you something about that later on. That model output is converted to a standard, i.e. CF compliant NetCDF file format. There's an example of a file shown to you there in Technicolor. We've been reducing that for selected experiments, selected variables, and selected frequencies. And I'll explain in more detail later on what I mean by selected in those cases. Once we produce that output, we upload it to the Centre for Environmental Data Analysis, CEDA, the node, which is the UK node of ESGF, the Earth System Grid Federation. And this is the means by which the CMIP6 data is made available to analysts and theoreticians and climate scientists all over the world. So once it's up there, anybody can look at it. The URL for CEDA is given there, and if those of you who have been there will know that that's a searchable interface, so you can look for different models, you can look for different variables, you can look for different experiments, and you can download the data from that location as well. At the moment, if you walk up there and ask how many data sets have been produced from the UK, in collaboration between NERC and the Hadley Centre, we'll see there's about 63,000 there. And here by data set, I mean a single variable on a specific MIP table from a realization of an experiment run using a model. So if any one of those things is changed, then it's a different data set. So that explains why we got so many of those things. And finally, I should say that the CEDA node contains, besides containing all the UK data that we've produced so far, it also has selected variables, the top 20, if you like, or top 80 variables from other institutions run by other models as well. But the whole of the ESGF has got all of the CMIP6 data uploaded already. So I said selected experiments. Let me tell you that for the three models that we're looking at, those are described here. So we've got an Earth System model, UKSM1, run at the N96 Orca 1 resolution, and then two resolutions of the HADGEM3 GC 3.1 physical climate model, a low resolution version run at the same resolution as UKSM1, and a higher resolution model as well. And in addition, there's data there from high-res-MIP, which is an even higher version of the HADGEM3 model. So for the Earth System, UK Earth System 1, we've got data up there for the DEC experiments. As you know, those consists of 4 experiments: PI control, 1% CO2, 4 times CO2, and AMIP, and also the historical experiments. And here I must apologise for a typo on my slide. We don't have 9 members of the historical ensemble for UKSM1. We've got 19. So apologies for that. I'll update that in the version of the slides that get distributed. For scenario experiments, we've got all of the tier 1 experiments, all of the tier 2 experiments, and for each one we've got at least 5 members of those experiments, and then also data for some experiments from selected MIPs, AirChem MIP, C4 MIP, LU MIP, GeoMIP, and RF MIP as well. For the low resolution version of HADGEM3, we've also got the DEC experiments. We've got 4 members of the historical. We've got 4 members of 3 tier 1 scenario experiments, and then some experiments from DA MIP, CF MIP, RF MIP, and high-res MIP as well. And then finally, for the higher resolution version of the physical model, we've got the DEC, and we've got 2 members of the historical ensemble as well. So that's what the experiments we've produced. Which variables have been produced, which variables and frequencies have been selected. Every variable that has been scientifically reviewed, that means that some scientist somewhere has looked at the variable before it's been uploaded, before we've converted it, and checked that it makes scientific sense. So if you're looking for a variable on CEDA and it's not there, it is possibly because it has not yet been reviewed. But we have made sure that all the ones that people apparently care about, we can have a question about what the variables are that people care about later on, those have all been reviewed, and I'll say a bit more about that in a second. At the moment, the only frequencies that we've got there are monthly and daily frequencies. So that's, again, what most people appear to be concerned about, but we will be adding sub-daily variables, so 6 hourly, 3 hourly and 1 hourly variables. We'll be putting those up there starting at the end of this month. We won't be doing that for all variables, we'll only be doing that for a subset, and basically that is dependent on what people have asked us for. So based in that same frame, in that same idea of people asking for variables, there's been various different lists of high priority variables requested by different people. So for example, there's a list of variables from the IPCC that have been designated as high priority variables. Currently, we've got 97% of those up on ESGF. There are 8 3-hourly variables to follow, which we'll be putting up starting at the end of this month. There are other lists from other areas of interest. For example, CMIP6. The impacts community are interested in a different set of variables. We've done 92% of those, and there's a few sub-daily variables to follow as well.
2 minutes,
and
Jeremy.
I put variables are available on request. So what I mean by that is if you don't see your favourite variable up there and you'd like to see it, then we are available to be requested. So do let us know. And finally, let me say that you can access more details about this from our website, which gives us progress in the way in which we've been uploading our data, the URL there. There's full details in the ESDoc system for the model description. There's also full details in the ESDoc system for data errata. So an important aspect of uploading the data is what to do when subsequently an error is discovered. There's an errata system, and so we advise you before downloading any data to check the errata to make sure that there's that so far nothing wrong has been found with that variable. And finally, there's an email address if you want questions or requests for more data. You can email us there. That's all I have to say. Thank you very much indeed.
Thank you, Jeremy. There was some disputing about your grammatical use of the word wither, but I'll leave that for the Google Docs.
I always like to have that question. Yes.
Okay, there's a couple of comments, but I'm going to ask one question first before the comments. And that is, you mentioned the IPCC, I think 81 or 88 most wanted variables. Now on the UK ESGF, there was going to be a replication of other models. So when you refer to that 97%, I presume that was UK data. Are you able to say how many other CMIP6 models that IPCC list has been replicated on the UK ESGF?
I can't say in detail. I know that there was an effort at CEDA to get as much of that list for as many of those variables as they could. And that work is ongoing. But it's also possible that there may be some gaps that need to be filled in. But CEDA are very responsive to that sort of request. So if people are expecting to see things there and they can't find them, then CEDA will fill in those gaps for you. Okay,
there's a comment about an ESGF holdings link in the chat that I think people can look at. Richard Wood notes that there's more monthly data coming, so more will be available in the future. The N216 or quarter model, will there be any SSP scenario data from that anytime soon?
I don't know the answer to that, Colin. I'm sorry.
Okay.
I can find out.
Maybe that can be followed up offline. Okay. I think the others are comments, so we're going to move on. Thank you, Jeremy.
Thank you.
Okay, so this is the final presentation of this session, and over to Laura Jackson from the Met Office. Laura, if you're in control of the screen, I'm going to hand over to you.
Hopefully in control of the screen. Yeah, okay. So this is a talk on the impact of ocean resolution at mean state and the rate of AMOC weakening, with a number of people involved. So we used 2 Met Office CMIP6 models with different horizontal ocean resolution. So that's HADGEM3, GC 3.1, the low resolutions, that's 1 degree, and medium resolution, that's 1/4 degree. And in particular, we've looked at the 1% CO2 increase scenarios. So what we find is that in the control, the medium resolution has a stronger AMOC, and it also has a greater weakening throughout the 1% run and throughout other scenarios as well, both in terms of the absolute weakening and fractional weakening. This is also true when you look at the AMOC in density space, and we're going to be doing the analysis in density space from now on. So the overturning circulation in density space is essentially equivalent to the transformation of density. So if you have light waters going northwards and dense waters coming southwards in the Atlantic, you're looking at, that's equivalent to the density transformation from those light to dense waters. And most of that transformation occurs through surface fluxes. So we can calculate the implied overturning from surface fluxes, which I'm calling F. And this is showing that F does reasonably approximate the AMOC at the beginning and the end of the 1% scenario. Oops, go back. So one advantage of doing this is that you can look at where those surface fluxes are occurring. So if you look at the low resolution, the medium resolution here, there's a lot of transformation of light to medium density waters in the east subpolar gyre, and then dense waters being transformed in the west subpolar gyre and in the Nordic seas. So if you compare the two, you can see that there's more transformation in the west subpolar gyre in the medium resolution run, and that at the end of the 1% run, this transformation basically switches off in both resolutions. And this is because we're getting reduced transport of heat in the ocean. So although both the ocean and the atmosphere warm, there is a reduced ocean atmosphere temperature gradient. So there's less heat loss and less density transformation, and that basically ends up switching off the dense water transformation in the west subpolar gyre. Now, because this is stronger in the medium resolution run, it has a greater impact on the total AMOC weakening. So we can see that the rate of AMOC weakening is related to the mean state. If we look at the mean state, essentially what we have is, so the Gulf Stream has warm salty waters. You turn to the North Atlantic current into the west-east subpolar gyre. Much of this recirculates around the subpolar gyre, and some of it goes northwards into the Nordic seas. And if you compare the medium resolution to the low resolution, you can see that medium resolution it's more saline. You can see in this figure, it's also warmer and it's also denser in the subpolar gyre. These figures here are showing this North Atlantic current, this sort of warm salty water coming northwards. You can see it's more westerly in position in the medium resolution than in the lower resolution. And also we haven't shown here is that it has the medium resolution has a stronger subpolar gyre, and it has less transport into the Nordic seas. This is all going to show that it appears in the medium resolution one, possibly because of the circulation differences, you're getting more of this warm salty water recirculating into the west subpolar gyre rather than the Nordic seas, and therefore that's where there's more dense transformation occurring. So we've also looked at the high-res MIP Primavera ensemble, and so this is looking at models with higher resolution, with different resolutions. If you look at this figure at the bottom, you can see again that the mean state is related to the change in the AMOC over the scenarios, and there's a good relationship in these models. The crosses, as opposed to the pluses, the crosses are higher resolution, and that's higher ocean resolution. I just noticed a chat thing which popped up. And the pluses are lower resolution. So you can see that the higher resolution models all have a stronger AMOC and a greater AMOC weakening. These models also have, if you look over on the other side, a stronger subpolar jar stream function, so that's a stronger recirculation. And they also have more saline waters in the west subpolar jar region over here. So these are all the dashed lines of the higher resolution models. And in this case, these are all higher ocean resolutions, though some of them have atmosphere resolution differences as well. So these all fit the idea that maybe in these models anyway, the model's resolution seems to be affecting the AMOC weakening, but that's because it's influencing the mean state, and that the mean state is affecting the AMOC weakening. One big caveat is that they all use the same ocean model, NEMO. So there could well be differences in different ocean models, different structural ocean models. Though I think it's more likely that the relationship between the mean state and the weakening is more robust than the influence between the resolution and the mean state. And I think I might have finished a bit early there. Hello?
Hello, yes, that's okay. You get an extra bonus of finishing early, which means hopefully more questions. So there was a little bit of discussion about the fact that the simulations have both increased ocean and atmosphere resolution. So are you able to say anything about whether it's predominantly an ocean resolution increase?
Okay, so yeah, so in our models, so the two models I showed the detail of, both the ocean and the atmosphere is different. But in the Primavera ensemble, so here I think I've only shown the, so there are some different ones of the HADGEM 3 models with the cross resolution. And in those ones, the results look essentially, it's the ocean which matters rather than the atmosphere. In terms of what's happening with the AMOC, it seems to be predominantly the ocean. That's the resolution, which is the important thing.
Okay, there's a follow-up question along these lines from Rick Williams, which is the atmosphere different in these runs? Well, the answer, I think you just said yes. But what Rick is interested in, given the ocean changes, is there any feedback from the differing ocean response on things like the atmospheric jet stream?
Don't know. Very possibly. Haven't looked at that at all.
All right. I think that I had a similar question.
So in terms of Primavera, there's a lot of other people who've looked at Primavera, these runs in different aspects. So there may well be people who've looked at that, but I don't know the answers.
Okay. So along the same lines, I had a question about the increased weakening in the higher resolution AMOC. In the higher resolution, does that increased weakening have large impacts on other aspects of the climate system response? You could imagine downstream over Europe a bigger response if there's AMOC.
Yeah, again, I think that's an interesting question and something I think it would be good to look at. I mean, so I should point out that the equilibrium climate sensitivity and the sort of TCR are quite similar in both these runs. There are slight differences. So it maybe doesn't have a huge effect globally, but it might have a regional effect. So yeah, I mean that's definitely how you pull apart what's simply due to the AMOC weakening and how much is other things might be difficult.
Okay, a question from John Brun. Do you see any oscillatory modes in the AMOC?
So obviously not in this paper. I haven't looked at that. So Malcolm Roberts has a paper. I don't think we didn't look at variability in that, but there is definitely some variability in the AMOC. Yes, in terms of the weakening we're seeing in these 1% runs, we've actually looked at there's an ensemble of sort of 3 to 4 members, and they're quite clearly significantly different to the two ensembles. So it's not just it's not just due to variability, the differences.
Okay. A question from Kath Senior: will we have enough different ocean models with high, low resolution comparisons to test?
I don't know.
whether
It's a
these
question.
results are robust?
Yeah, I don't know. And I have some ideas about looking at CMIP6 models. I think it would be, I would like to look at it. I mean, hopefully I can look at the relationship between the mean state and the AMOC weakening in more detail across the models, whether there's sufficient models of higher resolution which aren't just NEMO models. I don't know.
Okay, there's a couple of comments, but which I'm going to leave as comments. I've got one more question, and then I think we're done. And that is that the differences you see in, for example, the subpolar gyre circulation and even the salinity structure in I guess the Labrador Sea in that area. Is there any way to constrain any of this with observations to discriminate if one model is more?
So yeah, I mean that's a good question. So that's a part of. So I should say this is a paper which is undergoing reviews at the moment, and there's a whole section in that paper which I didn't include in this talk, which was doing some sort of basic comparisons, and you know, in some ways the medium resolution is definitely better, but in other ways the low resolution is better, and it's not clear what exactly is the most important thing to constrain. So I think it's an open question at the moment, actually.
Okay, great. Right, thank you very much, Laura. So that concludes this session.